Well, let's get you guys started here today. If you're looking there on the syllabus, you'll notice that we had really only scheduled one day for Chapter 3. We did a lot of talking on Chapter 3, although didn't quite get a chance to really do any concrete examples. We did one. Let's look at another 3. I think it's worth taking the time, although I think the best way to learn these new vectors or this new math that we were trying to get accomplished in Chapter 3 is really to begin to use them in our physics, which is Chapter 4. So the reason we only had a small amount of time for Chapter 3 was because, well, it wasn't really physics, it was math, but for some of you it was new math, that's for sure. And the other big reason, though, is that we'll take that math and we'll begin to apply it in Chapter 4. So I think it's best we get into Chapter 4, the sooner the better. That being said then, as I mentioned, let's kind of just recap. What did we do last time? What was the whole point of Chapter 3? And it really was to get us ready for Chapter 4. If you remember, I started off with this question. If a car is going 20 meters per second north and a second later it's going 20 meters per second east, did it accelerate? Yeah. How much did it accelerate? And if you remember, finally at the end, we came up with 28 and change there in a direction and went through all of that. So those little I-hats added to our mathematics. And so now we have things like, okay, the velocity is, or the acceleration is, or the, and I haven't used this notation quite yet, but we will as we get started, the position is. And there'll be something then with an I hat and then a J hat. And likewise here, there'll be something with an I hat and then something with a J hat. And something here, which will be an I hat, and something here, which will be a J hat. And the whole point here of that lecture was to get you familiar with what we call the unit vectors. And that I hat we treat like a number or a unit. We treat all of those with the same mathematical properties. So if I was putting this in terms of notations, I'm going to just throw out a new notation that we're going to see as we get started here in Chapter 4 in a few minutes, is that then we'll say the velocity has two parts to it. The velocity has an x component, which is a measurement of how much is it moving on the x-axis, and a y component. And that will be the symbols that we will use, a vx and a vy. And just for completeness, I'll put these out here, and this will kind of set us up for the beginning of Chapter 4. And that was the idea of Chapter 3, was to say then that as we get with two-dimensional motion, as things begin to move both x and y, we need a way to mathematically describe that in a way that will work consistently with we doing our calculations. And that was the point of this. Well, let's look at example number 8 here. 8, I think, no, I'm sorry. 8 is the one I said would be the same as, and I'll skip over. There's a helicopter one here. Is it 30? Maybe it's 31 here. But 8 is kind of a simpler case of 31. I thought you guys were ready to go to 31. Yeah, here we go. Here's a view of a couple of forces here. And so maybe I will begin with asking this question. Even though this semester we haven't done much with force yet, that's certainly coming up. That's what Chapter 5 is all about. But would force, which you guys remember from your Physics 102, would you classify that as a vector or a scalar? And why? A vector. Why?
Because like acceleration has direction.
Okay, fair enough. I was going down a different road, but yeah, force is connected to acceleration, and acceleration has direction. Okay, well.
But force has to have direction?
Yeah. What I would say is anytime we come across a quantity, ask yourself, does it make sense and does it make a difference if you add a direction like north-south? Is there something different about a force pushing something to the north versus pushing to the south? Yeah, you get a different result, right? Obviously, if that thing was stationary and you push it to the north, it moves to the north if you push it hard enough. You push it to the south, it moves to the south. You get a different result. So does direction matter? Absolutely. And so some of our quantities, directions matter, and so we call those vectors. And so these, like direction, doesn't matter when class is over and you're going to your next class or your car or lab and you go east versus west. Does it matter what direction you head? Absolutely. So is direction or position a vector? Yes. Velocity, does it matter when you're going to school and you get on the freeway if you go northbound on the 101 versus southbound on the 101? Absolutely, it's a vector, right? Acceleration and force, we can say the same thing. But other things, it doesn't matter. If we look outside and go, what is the temperature? I go, oh, well, it's kind of a cool day, at least a cool winter day for us in Santa Barbara. So we go, oh, it was cold this morning. It was, I think, what, 52 degrees. And I actually had to put on a hoodie. I doubt if many of you put on pants. Yeah, I see a bunch of shorts and flip-flops already. But actually I had to put on a sweatshirt. It was cold enough for that. But does direction make any sense with that? Would I say the temperature is 52 to the north? 52 to the south? None of that makes sense. So again, some things are vectors, some things are scalars. That's what we need to make a distinction with, and that's what we're learning this mathematics. So maybe I'll put it here for completeness, but again, not really doing anything or too much with forces until we get to chapter 5. But some things are vectors, others are not, and that's what we're learning with the mathematics. So this one has two forces on a mule. And let's read this here. It says a helicopter view, number 31, shows two people pulling on this stubborn mule. Find A, the single force that is equivalent to this force. That's just kind of a fancy way of saying, could you put these two forces together? What are these two equal to? Okay, and so they show us. They show us that one person is pushing with a force of 80, the other is 120. So is the equivalent of these 200? Doesn't 80 and 120 make 200? Yeah, only if they're in the same direction, right? It's more complicated than that. And again, that's what this beginning part is trying to illustrate here. So I'll put here number 31, and I will write out in kind of a vector form, and I'll put a little arrowhead over this and say, what are they trying to say here mathematically describing force number 1? Now in the picture they show force number 1 with a magnitude of 120, but it is angled at 60 degrees from the x-axis. And so drawing a picture of force number 1 and putting an angle of 60 degrees, how would I get the I component, the x component? How much of this force is in the x direction? Well, making a little triangle, that I would say is how much force is in the x direction. And it would then be adjacent to the 60 degrees. So I would write this then as the magnitude times the cosine of the angle. And then I would have my magnitude component with the direction. And of course, that's not the whole story. This force is not just pulling in the x direction. It's pulling in, a combination of x and y here in that first quadrant. So what I would say that this force is also pulling in the y direction. And so as I look over here, I would kind of look at this little triangle that formed and say, okay, the hypotenuse is 120. The vertical piece is this piece, which is opposite of this angle of 60 degrees, so I will put 120 and sine of 60 degrees. And so that's a good opportunity then to grab my calculator and go, okay, what is 120 times the cosine of 60 degrees? Oh, that should be a half, so that should just be 60. So that's 60 newtons. The other one is 120 times the sine of 60, and that gives me 104 newtons J hat. And so that would kind of be my first step, is to say, okay, I have been given the forces in polar coordinates. I have been giving it magnitude and direction. But how much of it is X and how much of it is Y? And that was what I was trying to say on Monday, your first step. Convert it from polar coordinates into Cartesian coordinates here. And the reason for that is I want to combine them together. And to do that, I have to put X's with X's and Y's with Y's. And so I've got my first step. How much of force number 1 is made up of its components, its X and Y component. And let's do the same thing now for force number 2. We could even draw it here in the diagram if it helps us look at it. I'll draw the arrowhead a little shorter because it says it's a force of only 80 newtons, and the angle is given from the negative x-axis. I'll keep that in mind as I go to do my calculation here. Because again, I would say the same thing, that this force, in order to be manipulated in any way, I need to find out how much is in the X and how much is in the Y. And so they've given me the numbers in what I would call polar coordinates, but I'm going to convert them into Cartesian. So in this case, making a little triangle out of force number 2, I would say that the X component is adjacent to that 75 degrees. So I will take 80, I will multiply it by cosine of 75, but I'll do one more thing before I'm done, and that's the direction part of it. It is in the negative X direction. So this is the magnitude, this factor gives me the component, and this factor gives me the direction. So there's my magnitude, component, and direction that you will hear me say again and again every time we keep doing our vectors. And in the Y direction, same thing. It's got a force here of 80, and maybe I should have put newtons there, newtons here. And in this case, I want the sine of 75 degrees. I would like to know how much of this is in the vertical direction. And I'll just, for completeness, put a plus sign there. Of course, mathematically, we never put a plus sign when we mean plus sign. But again, that's the direction. As I look at that one, it is lifting it in the positive Y direction. And so now, using my calculator, I can put in the 80 and multiply it by cosine of 75 degrees and come up with a negative, roughly, 21 newtons in the I hat direction. And so that is saying that the second person that is pulling on this mule is, pulling X. And that one is pulling positive X. And I guess that's okay. The two X's are balancing each other. I'm not quite. You can see that this person here has more in the X direction than that one. So that's going to, I guess, be having the mule get tugged a little bit in the X direction. To me, it kind of looks like that's not their intent. It looks like their intent is all about trying to move it in the Y direction. And so fortunately, each component is a positive in the Y direction. So let me take 80, multiply sine of 75, and I get about a 77 newtons in the J hat direction. And so adding them together, calling it the resultant, although what we will soon do in chapter 5 is say, when you add up all the forces, let's call that the net force. You might remember that from 102. But let's add them together. And again, the whole point is to say, let's take and put x's with x's. You cannot combine our vectors until we break them down into their Cartesian coordinates. That's the whole reason why this 120 cannot be combined with that 80 to give me 200. It won't come out to be 200. But in this case, a 60 minus a 21 is 39. So I have 39 newtons in the I-hat direction. And the 104 with the 77 is what, 81 there? 181 newtons in the J-hat direction. And so there is the net force. If I put that in terms of a picture, I might even just make a little parallelogram. And as we said here on Monday, then a line down that diagonal is the sum of the two, and the other diagonal is the difference of the two. And so that kind of looks like what I have number-wise. It goes up 181 and over 39. And so those two forces are equivalent to that. Now, probably should finish the problem with answering what is the magnitude of this whole force and the direction. In other words, finish with terms of a polar coordinate here. So I would take the 39 and I would square it. I'll take the 181, I will square it. I will take the square root of all of that, and now I will go from my Cartesian coordinates into my polar coordinates. So 39 squared added to 181 squared, taking the square root of all of that, and we're at about 185. So 185 newtons then is the resultant force. And so again, notice it's not 200. 20 and 80 do not necessarily make 200. In fact, they would only make 200 if they were in the same direction. And that's the important part of working with vectors and arrowheads, and that's what this math will allow us to do. I can get an angle here. Why don't I measure the angle being from off of straight down the road or up the center there, because this is going to get pulled. Actually, there is a Y in the road I didn't notice, so maybe it is better there's a slight force over in that direction, assuming they're trying to move it forward and in that direction there. So here I can look at the tangent of theta to say, okay, how much are we pulling this? 185. What angle is it? Well, it's not quite straight north or Y direction. I don't know if that's north or not, but the Y direction. It's a little bit to the right of the Y direction. And so in this case, and again, maybe it's best to see it with a different color, if I take that blue line and I make a right triangle out of it on my grid here, I will then say that the tangent is the opposite piece. And so 39, although that's the x component, is the opposite of that angle. So I'll say it again as we looked on Monday's lecture. Don't always think that the tangent has to be made with a y over an x. It can be an x over a y if you're looking at an angle that is different than the angle from the x-axis, as you first learned in your math class. And this is a good example of that. I am looking at an angle not from the x-axis, but from the y-axis. And so opposite of that is the x component. Adjacent to it, then, is the y component. So it's opposite over adjacent. And so now I can get my calculator out and go inverse tangent of 39 divided by 181, coming up with an angle of about 12 degrees. And that kind of fits my picture really well. Just kind of off to the side a little bit. I think there's more to this. What was that? A, find the single force that is equivalent to this, and B, the force that a third person would have to exert on the mule in order to make the resultant force equal to be 0. I probably think this would be a better problem if they said the third force would not be a person, but what would the mule have to do in order to not move? You've got these two people pulling on it, so what's the mule going to do if the mule doesn't want to move?
If we put the angle in, do you have to have like the direction?
During a test, please put where you are measuring it from. You can either spell it out or put it in your diagram. Usually there's something in the mathematics that make it very clear for me as I'm reading the problem. I can read the intent of what you mean by the angle based on how you set up your picture. But I would encourage you to leave no doubt. If you say it's 12 degrees, you say 12 degrees from the y-axis, and you put it there. And then there's no doubt in my mind where you're measuring it from. But when you leave that off, what I often do then is jump over to your picture and say, okay, how did they label their picture? And usually then it becomes pretty clear. I don't deliberately just take off because you don't have it there. That's not my intent, but I do need some evidence of what the thinking is in your brain, and so I will scour your work and go, okay, it's very clear at this point in their work what they are thinking, and they deserve credit for that. But if I don't find anything that gives me that evidence, I'd say, well, okay, I'm going to have to take points off. They may be doing it right, they may not, I don't really know. Yeah. Now, usually, of course, then if the answer is completely right, it's like, well, yeah, they must have done it correctly here, and they got the right answer. So I don't have to scour the work too hard when you get the right answer. It's when you get the wrong answer, and I'm like, okay, now how much partial credit do they get? Do they get a lot or a little? And then I have to look at every little piece that you have in there, and anything that's not there, then I obviously can't give you credit for it. So that's why I always encourage. Write things out on that test, write what you're thinking down, and you'll probably end up getting, if you don't get it all the way right, you'll get a lot of partial credit. All right. So this one, the part B anyways, is basically saying that if you were going to add this first force and this second force, and now you're coming along and adding a third force, which they in the problem says it's the third person. I'm going to say it's the mule here. What does the mule need to do in order for this not to move? Well, again, maybe we're getting a little bit ahead of ourselves. We haven't really done Newton's second law of motion here, but you did it in Physics 121. If something's not going to move, what do you know about those forces? Yeah, they got to go to 0. So they're using this really to teach you more about math than they are physics at this point, but they're also relying that you remember that from your Physics 102 class here, and that's the key. They even say, so the force equals to 0, just in case you didn't remember that. But that's actually kind of nice here, because didn't I just already do 1 and 2 added together? And so basically what you're saying here is force number 3. The force needed to keep the mule from moving would be the negative of 1 and 2 put together. And 1 and 2 put together I've already done here in part A. And so how we want to describe it, I guess we have our two options here. If we do it in the Cartesian coordinates, which were back here, I guess that third force would have to be a small amount in the negative x direction to balance the small positive amount from those other two people. And you would have to have quite a big negative y direction to balance the kind of big forward y direction. So that would be the force in terms of Cartesian coordinates. In terms of polar coordinates, I would say it just needs to be the same magnitude, but opposite in direction. And so opposite of that blue line is something that looks like that. Of course, then we want to describe the angle measured from where. Your choice. I think maybe that's probably the best thing to do, since we've already decided that that is an angle of 12, and we can apply our geometry, our vertical angles, and say that angle is going to be 12. So again, it would be at an angle of 12 degrees, and again, hopefully do more than just put it in your picture. I would say from, and maybe I'd put the negative y-axis here. And say, okay, it's negative in that direction. Or you could go to the more traditional measuring from the x-axis, and what would be 90 plus 12, 102. And it's in a clockwise direction, so if you wanted to put negative 102, that would kind of be the traditional way of describing the angle. So got a lot of options there, and so my point is that you are understanding and read them. I don't care if you measure from the x-axis, the y-axis. However, just make it clear that you know what it is, so I can give you full credit for it. That's the idea here. They were even nice here. In case you forgot, the units of newtons or the units of force are in newtons. Yeah.
Why wouldn't it be
Oh, well, when you do a polar coordinate, r is never a negative number. Right? R is the magnitude. This is a positive. Yeah. So, yeah, putting a negative here, that's not that big of a deal to me, because I kind of get what you're after. But polar coordinates, we never describe distance with a negative number. It's how far from the origin and then what angle. Yeah. And so you don't have any negative r values in a polar grid. Well, like I said, I want to do 3 examples. We did one on Wednesday. We were able to work one in here. Let's do one more, and then we really should see how all this works in terms of our physics. Here's a good one, number 51. It'll again hopefully allow you to begin to see the power of these little I hats and J hat notation. And that's, again, what I want to get across here. And then, of course, start to use them in our physics. And so this example uses the vector of position, whereas the last one I just did clearly was using the vector of forces. And like I said, maybe even a little premature, since we haven't done any forces in our physics class yet this semester, but I don't think that was overwhelming. You would probably remember most of that from 102. But position 2 is a vector, and so let's talk about this. Read it through here. Here we have a ferry boat, and it transports tourists among 3 different islands. It sails from the first island to the second, and they tell us it's 4.76 kilometers away. It's a direction of 37 degrees north of east. It then sails from the second island to the third island in a direction of 39 degrees west of north. But notice it didn't say how far it was. Well, let's keep going. Then it sails from the second... Oh, I just did that. Finally, it returns to the first island, sailing in a direction that is 28 degrees east of south. Again, notice they didn't tell me the direction. Calculate the distance between the second and third island, and then B between the first and the third island. Okay, so let's see if I follow this correctly. They've given me some information, and so let's study that. Let me put a little circle and call. Okay, here is island number 1. And let's do our standard compass rose here, where this will be north and east waffles. And let's see, never eat soggy waffles. I got to keep going back to my kindergarten there. Okay, well, how do I get the compass rose there? And so as I look at this first one, that's the one that gave me the most information here, where they actually tell me both a distance and a direction. That's a polar coordinate, right? The distance is 4.76. The direction is 37 north of east. Well, maybe we should talk about that. What does 37 degrees north of east mean? Yeah, they're really saying 37 degrees north of due east. So due east would be like the x-axis. And then we're going to be 37 degrees north of that. So I'll go ahead and say, okay, here's that first little motion. It is 4.76 kilometers. It is 37 degrees. That is going to get me to island number 2. And I'm not going to worry. I'll just measure things from maybe the center of the island. I know the ferry's not going to really go to the center of the island. No, so maybe I should do a port. I don't know. Should I put the grid right here at the edge where the water would have been? Anybody care? Is it that particular? No. All right. Probably would look better that way. All right. So I can't resist. All right. So there is island 1. There is island 2. So we are going to go from some harbor or port or pier on island 1 to some harbor or port or pier on island 2. Okay? And so they give me the angle and they give me the distance. Okay, fair enough. But then notice what they say on this second little part of it. It then sails to the second island, in a direction. It then sails from the second island to the third island in a direction that is 69 degrees west of north. Okay, so here's due north. They are saying (69 degrees west of north, west of due north. 69 degrees west of due north. And so I head off in this direction going to island number 3. What they didn't tell me, though, is how far away that island is. Well, let me put an unknown here. And I'll draw a line to represent its distance. I'm a little bit uncertain how long to draw it in this picture, but I do know they say something about the direction for number 3. It says, finally, it returns from the first island, sailing in a direction that is 28 degrees east of south. All right, so straight down on my picture here is south, and we're going to go 28 degrees from that. And it's to the east. So that tells me the third island is not here, because here you would have to go a little bit up to the west to get back. This third island's going to be after over here somewhere, because I've got to come down here. All right, so over here somewhere is island 3. And so we're going to have to sail to island 3 so that when we return trip, we can angle it at 28 degrees to the east of due south. And so I think you're catching this on, you probably did long before you started this class, is there's a lot more to doing a physics problem than just the mathematics. I mean, the mathematics is there, definitely. But there's 2 other big steps there, and that is, number 1, what I call just reading comprehension. Can you read the problem? And I read it again and again and again. and make sure you understand what they are describing for you. That's a big step. And then once you get that, then you have to convert that into equations. Then finally you get to do the math to answer the question. Okay, and so that reading comprehension and that conversion, if you will, that converting from one into another is really an important piece. All right, so just so that I can have some unknowns listed up here, why don't I call this length A and this length B? How about that? And so the distance from 2 to 3 is A, from 3 back to 1 is B, and those were the two questions that were asked here. What is the distance between these islands? Between the 2 and the 3, which wasn't given, and between 3 and the 1, which wasn't given. Well, I guess I would describe this really as 3 little vectors, right? Let's talk about this first one. This first one, let me refer to it as displacement or movement of number 1. Let me give it an R for a symbol, because that's what we're going to use for the position vector as we get started here in chapter 4. So let me just kind of use that now. But as I look at this, shouldn't there be an I hat component and a J hat component? And this one, I think you have the idea behind it that, yeah, this vector, this island, is off so far to the east and up so far to the north. And to get those, you would say, make a triangle. And maybe a different color could even help us visualize the triangle. But that's what's meant by Cartesian coordinates. So again, notice the description is given us in polar coordinates. I'm converting it first into Cartesian coordinates. Why? Because as you move, you got to put x's with x's and y's with y's. And so I have to know how much of this motion is in the x and y components, not how much is in the polar one. And so in this case, I would take the 4.76 and I would multiply it by the cosine of 37 degrees. That would be how much you moved to the east, the x direction. And likewise, to the north, or the y direction, 4.76, and then I would have sine of 37 degrees. And if I get out my calculator at this point, I'll actually have some numbers to work with. 4.76 times the cosine of 37 degrees is about a 3.80 kilometers in the eastern direction. And the 4.76 times the sine of 37 degrees comes out to be 2.84 kilometers in the J direction. And that's probably the easiest one to work with, because then I would say, what about motion number 2, going from the second to the third island? Now again, I would have an I component and a J component. How much does this represent in terms of the horizontal and vertical axis? So starting here and looking at this vector, you can see it's kind of angled off. They gave me this angle as 39 degrees. So if I wanted to know how much did it move in the x direction, I would make a little triangle out of this. And say the x direction would be here. This would be the hypotenuse. Now I don't know the hypotenuse, that's what I'd like to find, what is A, but it would be A times the opposite of the 39 degrees. So that would tell me that this should be A times the sine of, 69 degrees, not 39, 69 degrees. And so that's how much it would be. But it would also be in the negative direction. I guess I should have put that, give myself a little more space. But that's what I was saying here. Magnitude component direction. This is the movement of it. It's in a negative I hat direction. It's this much. This is the hypotenuse, and that's the component of it. Likewise, for the vertical direction, it would be A, and then it would be adjacent to the 69 degrees. And it would be an upward or a northern, so it's a positive there. So if I get out my calculator here and just write in the sine of 69 degrees, that is 0.9, I'll just do 34, and that would be A in the I hat direction with a negative. And likewise, the cosine of 69 is 0.358 A j hat direction. Of course, I don't have a complete number here. I can't because I don't know what A is, but that's obviously how I would mathematically describe it if I knew what A is. And then likely, or likewise, I should say, the third motion, same idea. There should be represented how much does it move in the x-axis and how much does it move in the y-axis. And so again, making a little triangle out of this so I can kind of visualize this motion, I will see that in the vertical direction it's down, and in the horizontal direction it is a positive amount. And so this would be written as a B times sine of 28 degrees, because again the sine function is because it's opposite of the 28. That gives me the x component. The positive, of course, is because that motion is to the right. Same thing in the vertical direction here. I would have a B and I would multiply it by the cosine of the 28 degrees. Again, the cosine, because this part I want, the vertical part, is adjacent to the 28. Cosine gives me adjacent. It's also downward, so I would put a negative there. And like the one above it, I can't really solve much for this other than figuring out what is the sine of 28 degrees. And that comes out to be a 0.469 times B for the I hat direction. And then the cosine of 28 degrees is a 0.883 B j hat direction. And that's the part I really want to illustrate. This is how I would use the components, the I and J components. Again, that's the point of this chapter, the mathematics behind all of this. Now, to finish the problem, I am going to have to read a little bit of the physics. What am I going to do with all this now? How am I going to get A and B now that I've done this much work? Is there anything I know from this physical description? Yeah?
Yeah, like some triangles on the inside of the triangle.
Fair enough, I do. And I can do all kinds of things with triangles. I could use law of cosines and law of sines, and you probably did that a lot in your math class. That's not the intent here, though, at all. Yeah?
The x directions and the y directions, of course, are equal to 0.
Yeah. If you were to add all these together, vector 1 plus vector 2 plus vector 3, don't you get back where you started? The total movement is 0. Right? You're back where you started. This fairy has not moved left or right or up or down, or maybe I should say east and west and north and south. So that means when I add these, I should get 0. So 3.80 minus 0.934A plus 0.469B should come out to be 0, right? And the y component should come out to be 0. And so the other option here is 2.84 plus 0.358A minus 883b is equal to 0. And now, don't I have two equations with two unknowns? We're back to algebra 1. Or is that algebra 2? Maybe that's algebra. Oh, we're back to some algebra here, right? And then we can make a decision how we want to solve this. Maybe by substitution, elimination, Kramer's rule, plug and chug and final. We wouldn't want to do that. But we've learned a bunch of options along on how to get A and B. But for us, and in the interest of time, I'm going to stop there and say, now we got some math. I know you know how to do the math there. Can't hurt to have more practice. I'll leave it there and have you practice solving for A and B. But when you solve for A and B, then you have it. You have the first answer, A, how far is it from 2 to 3? And then B, how far is it from 3 to 1, right? That's this idea. But as we get into some more examples, like I said, let me get us into and starting with chapter 4 here. And here's why. Chapter 4 can be summarized as saying it is putting together the last 3 chapters. You'll see as we do some problems here in chapter 3, there'll be problems where they give us distances, say in centimeters, but they want the answer in meters. Or they give us the distance in miles, but they want the answer in meters. So we're going to have to do some unit conversion. Well, we did a lot of that back in chapter 1. Okay, fair enough. You'll also see they ask questions about position, velocity, acceleration, time. What is the meaning of all those? How are those connected? Aren't those the things we did in chapter 2? But what's different here in chapter 4 is our objects will be moving in 2 dimensions. We'll do something like toss a rock into a lake. And so as we look at the motion, yes, there is a position on the x-axis, but there's also a position on the y-axis. And so that stuff we were doing in chapter 2 is going to be extended to not just a one-dimensional motion, but a two-dimensional motion. How are we going to handle two-dimensional motion? Well, that's why we learn these I hats and J hats of chapter 3. So if we add our motion and our kinematics that we learned in chapter 2 together with the math that will allow us to do both an X and Y motion at the same time, we actually have the answer here to chapter 4. And so chapter 4 is really the chapter that you want to keep focused on and make sure you can do, because that's where the test will be. The test will be putting everything together. And so I think you will find chapter 4 with all those pieces of chapters 1, 2, and 3. And for some of you, then it will be an easy chapter. You'll go, well, yeah, we did all this. I just got to put it together. Others of you will definitely say, oh, yeah, this is definitely the hardest chapter we've done so far. You won't finish the semester thinking chapter 4 was the hardest one. I can guarantee that. But you will get to chapter 4 and go, yeah, this is hard because I got to do all these things all at the same time. And so just again, organizing your thoughts is a big step here. In fact, where I want to begin is really to take you back to Physics 102 and really ask this question: how to do a physics problem in 2 dimensions. And so if we toss a rock across the ground and into the pond, or I'll just do an eraser across the room, how are we going to handle 2-dimensional motion? And I hope what you learned in 102, and I'll illustrate again here in a few moments, is that you are really going to do 1-dimensional motion, but you are going to do it twice. We like to say nature has kept X motion separate and independent from Y motion. Yes, both are happening at the same time, but they are independent of each other. And that's what you saw if you had me for 102, and I would assume you saw a few of these experiments with Dr. Kelly if you had Dr. Kelly for 102, or whatever your high school or other school where you took physics. Watch this to illustrate my point. Here, these two objects mount on this crazy contraption. One of these spheres is just solid. I will put it on the edge. You can hopefully see then when I release this lever, and I won't do it all the way, but this spring will push the shaft against the sphere, and this little ball will be kicked off to the side. Fair enough? Let's look at the other one. The other one has a borehole drilled in it so that I can put the shaft through that borehole. And so when I release that one, the shaft, as it pulls out, will just let it fall straight down. So I would say this one here is just one-dimensional motion. It is the stuff that we've been working with in Chapter 2. And you're probably getting pretty good at that. Whereas this one is the new piece of the puzzle. This is the one that when it gets kicked off to the side, it has a horizontal motion right at the get-go, but what else happens once it gets kicked to the side? Gravity pulls it down, and so that one's going to have a two-dimensional motion to it. But here's what I want you to see, and it's kind of hard for you guys way back in the room, so we've got a high-tech, less accurate one over here. I should say high-tech, expensive, less accurate one over here. But this low-tech one, it works really, really well. And what I want you to see here is that when I release these, one of them is going to fall straight down. The other one has a horizontal motion while it is falling down. But at any given moment in time, you will see that these two have fallen down exactly the same distance. And the physics I'm trying to illustrate here is that even though this ball has an X motion, a horizontal motion, how does it affect my calculations and my mathematics in the vertical direction? It doesn't. This is my point I'm trying to say. To do two-dimensional motion, what I'm going to do is let X's go with X's and Y's go with Y's. You can begin to see now why we just did Chapter 3, and we had all this fancy math that will allow us to keep X's with X's and Y's with Y's. The whole point is that's the way nature behaves. So we need a mathematics that describes that. And that's what we just did. We've learned some mathematics that will allow us to say anything that has to do with X's, keep it together and work with them. Anything that does with Y's, keep those together and work with them. But do not cross the X's with the Y's. And so I want to illustrate that even though this ball has a horizontal motion to begin with, its vertical motion to begin with is zero, just like that ball. In terms of vertical motion, these two are identical. The only difference is this one at the same time will have an X motion. And so tell me if these two do not hit at the same time. They do hit at the same time. 1, 2, 3. And at least for those of you close enough, didn't they hit at the same time? In fact, let me do it a second time to illustrate it yet again. But this time, let me pull the shaft back a little bit further. And I'll put it on this second knob here. And so when I put that one on the shaft and this one off to the side, perhaps you see what's going to happen here is this time it's going to be pushed harder. And so it's going to fall down and land there. But rest assured, here's the point I want you to see. The fact that it has a horizontal speed the last time and this time has more horizontal speed, how does that affect its vertical motion? It does not, exactly. And so what's going to make Chapter 4 hopefully easy for you is you're not going to do anything different this chapter that you didn't already do in Chapter 2. The only thing you're going to do for the two-dimensional motion is you're going to do one-dimensional motion twice. You're going to have an equation that half of the equation has an I hat in it, and the other half of the equation is going to have a j hat in it. And those equations each represent one-dimensional motion, and they're going to be exactly the same equations that we've already been doing in Chapter 2. And so, again, nothing new, harder perhaps, because it's going to have to do both at the same time. And so we got to keep that in mind, that both of these motions happen at the same time. But again, watch this one and tell me if they don't hit at exactly the same time, even though this one has a horizontal speed, and even though it has a larger horizontal speed than it did before. 1, 2, 3. It did, right? And so they do, thank you. They do match here. Well, let me try this one. This one's always a fun one to do. It has a cannonball here, and inside has a cannon. I can push it in, and what will happen is that cannon can be released and then shoot the ball. The high-tech part of it's right here. The on switch goes up, and on this little edge here that is, I'm going to put it like this, facing you, there is an infrared beam between those two knobs. It's small enough that I can't get my finger in there, but if I get a piece of paper or something, and I break the beam, so I'm going to put the piece of paper in there, you'll hear it. And maybe those of you close enough can actually see the cannon shoot. So I'm going to put it on here, and the beam gets broken with this little post that's sticking up. You can't see it, but there's a knob sticking out this way. So when it goes through, it shoots the cannon. So here's the loaded cannon. It goes through, the cannon shoots. And so if the ball is in the cannon, it will go through and shoot the ball up. Fair enough? And if I've adjusted it right, this cannon should only push in the vertical direction. And it's push the ball up, whoa, and straight down, which it did not. So let me tighten this up a little bit and see if we can shoot the cannon straight up. A little better. Cannon straight up. Oh, that's looking good. All right. Fortunately, it's not always consistent, so I'm going to do it one more time. And I'm going to do it one more time. All right, maybe I'll do a little bit more. Thanks. All right. So, like I said, it's a fun one to see because everybody in class can see it, but it's not so accurate. All right, I'll try it again. All right. Liking that a little better? Liking that better? All right, so hopefully, that was straight up and down, it just popped out. Okay, so, but hopefully you get the idea that this cannon is going to give that cannon, the ball, a push, but it's only in the y direction. And what I want you to see then, and this hopefully will illustrate, how does it affect the motion in the x direction? Does not. Right? So, as this thing moves along, and I give it a push this way, when it approaches the trigger, doesn't the ball and the cart already have a motion in the x direction? And the cannon pushes on it vertically. How does that affect the x? It doesn't. And so that ball, even though it is now going up in the air, and then gravity pulls it down, which again is only in the vertical direction, does not affect its x. Hopefully then, as this thing goes back and forth, then as it moves along, the ball will have the same X direction that the cart has. So where does the ball land? What? How come it didn't fire? And let me pull it into here. All right. Well, maybe I'm not going to show you this very well today. Thanks. But I'm going to give it a try nonetheless. All right, so when it goes by the trigger. My trigger's not triggering. It almost needs like, yeah, a little more length to it. It's just barely missing. Maybe the track's bent right there. Yeah, I don't know if it's worth this much time. All right, let's try oh, thank you. All right. Yeah, and he's like, yay! It still sucks. All right. Yeah. I guess if it breaks, we're done.
There we go.
Yeah, okay, yeah. So finally, it went. And hopefully it will go again back here so I have a little more space, but if I give it even a faster push, yay! And it did go in, it just kind of ricocheted out there. And I'll try my luck a third time. Yay! Yeah, but hopefully you see the idea. Less than perfect, yes, but Diz hopefully getting the idea across. Another fun one to do, and we better get into the math here, but I could do the same thing at a little longer distance here. Here is a bullet. This bullet can go into this gun. I can breathe in and then shoot. And as I shoot it across the room, of course, gravity brings it down. But while I'm shooting it, let me try one more feature. I'll turn on this little electrical box. You can follow the wires across. They actually go over to this magnet right here. And so like the lab we did, it'll hold Bob here. Okay? But the other thing to notice here is this electricity is connected through this funky little switch up here at the top. And so as the bullet is exiting, it will lift up that little metal contraption and turn off the electricity. So what will happen to the can? Yeah, it should fall. It should, right. And the bullet should fall. And even though the bullet has a horizontal motion, the point is that doesn't change anything. They fall together at the same rate. So the only tricky part is to make sure I'm actually pointing at the can. Actually, it looks real good. Probably get a little more accuracy if I step back. Oh, good. Looking right at the can. So let me do a couple things. One, since I have a tendency to jar it when I'm blowing on it and move the barrel, let me kind of get a little rubber flap here, so hopefully when I do the blowing here, the gun won't shake. All right. The other thing here is let me get the bullet in here and bring it back. There we go. And so the bullet's all loaded. And that little switch right now was deactivated. Just connecting it will activate it here. Don't touch anything. There we go. And so now, hopefully, you don't know if you want to put your hands up there, but I tried to aim on the left side, so the ricochet should go towards the computer, not to the front row there. Yeah, and you got that one. All right. And so these low-tech ones just seem to be a little more consistent and accurate. All right, well, it's like I said, a fun little exercise, and I think probably most of you saw that in 102, and you get the idea. And I just wanted to use this as an opportunity to remind you of your physics in 102, because again, to summarize this class, I'd say, let's take the physical principles you learned in 102, together with all the math you have learned not only in your math class, but you're just learning now in this class, and put all those together, and we can solve some pretty complicated and involved problems. Much harder than anything else. Oh, I forgot the best part. Wow, look at that. But we got the little hunter's hat there. So let's do that. Let's go through some mathematics. And so maybe so you guys can see a little bit better, I'll take these things down. And actually, I should probably even turn off the power supply. And let's start to put our math together. And so, continuing on with this idea that what we're going to do is the mathematics of, or the motion of two dimensions using one dimension twice, this is what that mathematics will do really well for us. Watch this. If I were to take a grid, say X and then Y, and say here is some object, then I might describe that object by saying this is its position. You might even say its initial position. So there's my first notation for this chapter. What I was telling you earlier when we did the island problem, that let's describe where the object is in terms of this R. Kind of looks like a little polar coordinates. That's why we use it. In chapter 2, we used X because it was always just one dimension. Made sense here. And so I guess mathematically I would be describing this as R, and of course if this is initial, I'll just put R, would be X initial. That would represent how far over is it on the X-axis, and Y initial, J hat. All right? And so that is what I meant by putting together chapter 2 and chapter 3. What I really have is two equations here. Do you see that, right? I have an X and a Y. Now, if this thing were moving, so let's just say it kind of migrates along here, then I would use a little vector here describing where it is at that moment. Maybe I should write it as R without an initial or anything. If I did this, R is a function of time. Would that be an okay notation? I don't want you to think this is R multiplied by time. What I want you to get out of this is then this would mean that the horizontal position changes with time, and at the same moment, the vertical position changes with time. And some of these equations you're about to see on the board are going to look really long and complicated. Hopefully, we won't get too scared by this long set of equation and all these symbols. If you read them, you will begin to see they're not that complicated. They are exactly what we were talking about. They are two-dimensional motion, which involves one-dimensional twice. And that's really what I have. All I'm saying is there is some function of time of how the position changes, right? but it is also changing in the y direction. And so I have two functions, one describing where is it on the x-axis, and the other one describing where is it on the y-axis. That's all this fancy notation means, these little I hats, these j hats, these arrows, these parentheses. Okay? Yeah, begins to look a little intimidating, but really hopefully straightforward. In fact, maybe to make it look a little easier, we often just do this. And that has its advantages and disadvantages. I'll put a box around it. I think the advantage is we don't have to write the function of time in there. The disadvantage is we might forget that these are functions that change with time. The object's position is not just some number and that's it, end of story. It's not at position 3, 4. It could, but that would be something that's stationary, and that's kind of boring. That's not what we want to study. We want to study things in motion here and all the pieces that go with it. So as you'll see, me and your author, as you read them and do the problems, they'll describe the position vector like this. And of course, if it's moving, let's ask those same questions we asked in chapter 2. At what rate is it moving? Well, what are we really asking here? How quickly is it moving? What word should I put there? Velocity, right? You're really saying something like this. The velocity, and yes, it will be a vector here, is really saying how much did the position change in a given amount of time, right? And again, if we use our calculus, you might say, how is it changing its position in a very short moment in time? You remember this discussion we had in chapter 2? Didn't we do the same thing? We took a little longer in chapter 2 to kind of come up with it. But we said, look, if you kind of describe what you're trying to analyze, you're trying to say how quickly is it changing its position? What is its new position a moment later? And you want to know it at that instant. So you want to know as time goes to 0. And just like we did in chapter 2, what is this? What mathematical property did you just describe? Derivative. The derivative. And so as I said back in chapter 2, had you never been told that the derivative of position gives you velocity, you can figure it out based on what are you trying to describe to yourself. You're trying to say, I want to know the rate at which it is changing its position, and I want to know it at that instant. So there is the calculus, the limit as time goes to 0. And so I want to know the derivative of the position. And again, isn't this what we did in chapter 2? Now there is one subtlety here. We didn't have vectors. In fact, I bet in your calculus class you never took a derivative of a vector. However, I bet you could do it without me even showing you. Oh, don't fear, I will show you. So let's take that derivative here and let's think it through here. What you are really saying here is take the derivative with respect to time of the r vector. Now the r vector is this thing, which has an x that changes with time and has a y that changes with time. So even though you've never taken a derivative of a vector, I know you know a lot about derivatives. And one of the things you learned is that when you have two pieces or two terms, you can separate those two terms, right? That's part of the property that you called a linear operator. The derivative is a linear operator. You can separate it in those two pieces. Things like sine functions aren't. You can't. It would be great if the sine of a plus b was just the sine of a plus the sine of b. But you know it's not. It's that four-term identity. It's more complicated than that. But linear functions are just simply added together. So that's beautiful. In fact, there's something else here that even though you've never taken the derivative of a vector, I think you can get away with. What would you say, and this is kind of new here, so I'm going to ask about this I hat. What does it mean? And knowing that will hopefully answer the question, how do I take the derivative of it? Well, x and I together, doesn't this really mean multiplication? Okay, so if you have two functions multiplied together. Isn't that the product rule? I mean, don't you know how to take the derivative of two things multiplied together? I'll even do you one better. What would you say about the I-hat in terms of its functionality? It's a constant, right? What do you mean by I-hat? One unit in the x direction. Does that ever change? No. So how do you take a derivative when one of them is a constant? Let's pull it out front. Yay, there it is. Now I know we're at a step you know how to do, right? Take the derivative of that function. And in fact, just to keep it looking like we like to see the unit vector at the end of it, instead of pulling it out in front, as you often did in your calculus class, let me push the I-hat to the back. And so probably for most of you, this is the first time taking a derivative of a vector. But hopefully also you're seeing it's not beyond your skill level, right? It is really what you have learned. You've got two things added together. You take the derivative of the two terms separately. And one of them happens to be a constant, so you just pull it out in front. And so really I'm just taking the derivative of this function x. And likewise here, don't you see that same thing here with the y? So this should be dy dt. J hat. Let me keep going with this. And then let me also kind of read into the mathematics here. What would you call that? dx dt. Yeah, isn't this the rate at which it's changing in the x direction? And just the x direction. So I wouldn't call that its velocity, but it might be nice to call it the x component of the velocity. It's a measurement of how this thing is changing in the x direction, regardless of what it's doing in the y direction. It may be a big number or a small number. If it's an airplane kind of flying across, you can see them go up and down the coast all the time here. That number is probably a big number. It's changing in the x. And while it is changing in the x, what is the airplane doing in the y direction? Yeah, assuming it's already at altitude and flying along here, yeah, on our airspace, yeah, that would say a constant. So this other piece of the puzzle, again, is not the total velocity of it, but it's a component of its velocity, right? It is describing to me how does this airplane, or whatever the object is, change its position in the y direction, and the y direction only, regardless of what it's doing in the x direction. So this airplane may have this number very big and this number very small. A rocket that's fired straight up, and after it's been going for a while, this number here is probably very big. It is changing in the y direction by a lot. But if it's going straight up, it's not doing anything in the x direction. And so what I have, like I had here for position, I have chapter 2 twice. I have a description of my motion, two-dimensional motion, which is really taking one-dimensional motion but doing it twice. And so hopefully that will give you some confidence here as you go into chapter 4. This is going to be easy. I just have to do everything I did in chapter 2 twice. So however long it took you to do chapter 2, double it. Okay, keep that in mind. This could be a long chapter, and the problems can be long and detailed, because if it took you, say, 45 minutes to do a problem, it's probably now going to be an hour and a half problem, right? We got to do all that stuff just twice. And so hopefully, though, your skill level will build up and it won't take you quite as long as it did the first time you saw this. But that's the description here of what we're trying to say here, that there would be some motion, and that motion, that velocity vector, is made up of two pieces. How much does it move in the x? How much does it move in the y? And then, not a surprise, Because what's the next thing we did in chapter 2 after we said position, and after position we said at what rate is it changing in its position? We did what? Yeah, how is it changing its velocity, right? And it's kind of that same description. We said let's define acceleration. And so let's do that same thing, except now it's 2 dimensions. Meaning what? Well, velocity has components. So when you say, how does it change its velocity? You've got to be looking at both of those components. You would have to say, how does it change its velocity vector over a period of time? And if you wanted to know that in a short moment of time, you would then say, let's take the limit of that. And of course, that means you would have the derivative of the velocity vector. Exactly. So exactly the same thing we did in chapter 2, except we have these vectors, which hopefully you're seeing from chapter 3. These vectors really just are 2 functions. And so we're just doing what we did in chapter 2 twice. And you'll see it when you write it out here. If I take the derivative of the velocity vector, which, this is one of those ones I said, it begins to look pretty complicated here. But if it doesn't look complicated to you, great. That means you're just reading it. You're not lost in all the symbols. I mean, this has a subscript, and then it has these I hats and the J hats, and then it has these funny derivatives. If you got some extra time, put a function of time in here too. Oh, cut that out and put that on your refrigerator. Let your roommate see, this is what I'm doing in my class. What are you doing? And see if it makes any sense to them. But hopefully it's just the opposite to you. Hopefully it does not look real complicated. And that is because you are hopefully reading and understanding each step, not so much involved in the details of, is there a subscript? Is there a super subscript? Is there a hat? Is there a dot? What is this I? What is this J? And so when we get to this line, and I should emphasize, I'm just taking the derivative again of a vector. We did it once, but maybe it's worth reviewing since this is the second time you've taken a derivative of a vector. All I'm doing, the same here, is I am taking a derivative of 2 terms, so I separate it out. And then I am saying that the I hats and the J hats are a constant, so I can pull them either in front or behind of the derivative. We usually do them behind the derivative. And then I'm going to interpret my equation. I'm going to read it here. What are you really saying here? What does this term really say to you? Yeah. This is not the full velocity. We already said earlier on, this is how its position is changing. So that's why we call it the velocity in the x direction only, regardless of what the y direction is doing. So this is the velocity in the x direction. And what this is saying is, how is that velocity, the x velocity, changing? So it's not the whole velocity. It has nothing to do with the x part of it. It's separated out. And so probably the best description we can have of that is what we would call the acceleration in the x direction. And so we'll put an A with a subscript. And what we mean by that, acceleration in the x direction, is how does the x component of its speed change? Not the whole speed, just the x component. And of course, likewise, for the other term, what do we mean by this, which is the rate at which the velocity in the y direction changes with time? That's probably best described by calling it the acceleration in the y direction. It is not the whole acceleration. It has nothing to do with what's going on in the x. It has only a focus on the y's. And so again, this mathematics is allowing us to keep x's and y motion separately, which is why we did these little experiments, to show you that's what nature does. And so if we want to understand where this rock is going to land when we toss it, we need a mathematical way to calculate it And that mathematical way needs to represent what nature is doing. And these I-hats and these J-hats do it very, very well. And so that's why you're being introduced to it. And so I'll put a little box around it. And so I'm hoping that you see all I've done is taken the one-dimensional motion and doubled it, right? Instead of having an x, I have an x and a y. Instead of only having one velocity, I have a velocity in the x and a velocity in the y. Instead of having just one acceleration, I have an acceleration in the x and an acceleration in the y. Question?
Is there a lot of need to put the subscript of x or y and then also the like I hat and j hat? Aren't those both just referring to like what?
Okay, I would say that clearly if I don't have them, that this one is obviously going with the x and this one is obviously going to the y. But the problem with that is these could be very different numbers.
And you might accidentally equate them.
Right, and I look at those and I go, oh, those are the same thing. And they're not. This could be a big number and that could be a small number. I won't go as far as giving them their own symbol, like P and Q. But I will go as far as to say A with a subscript to indicate they are both accelerations, but they're not the same acceleration. Yeah. And as you'll see, sometimes it's nice just to say our only attention is focused on the x motion, so I'm just going to write the equation for that, blah, blah, blah. And then I just drop the I-hat altogether because, you know, everything in here is talking about the x motion anyways. And so we do that a lot. And then that will keep reminding me that this is only for the x motion, even though I don't have an I-hat in the equation. So it's preferred then that we do keep that subscript x to indicate not only are they different, but when we separate them from the I-hats, we don't forget that it's the x component. Yeah, good question. All right, well, this is probably then a good time to clear off this side edge over here and put really the whole idea of chapter 4 and show you what I keep saying, that chapter 4 is really this chapter 2 repeated twice. I have then this position vector, and it is connected to the velocity vector, which is connected to the acceleration vector. How do I get from position to velocity? I take the derivative. Doesn't that look familiar? Isn't that really exactly the same thing we did in chapter 2? The only thing I have added in that diagram is the little arrowheads over the top to remind myself and to remind you that there's really two equations in there. There is an I and a J. There is a motion in the x and a motion in the y. But other than that, this is the exact same diagram that we had in chapter 2. And so that's what I meant by earlier by saying this chapter, although can be twice as hard and twice as long as chapter 2, is really putting everything together. Put the mathematics of these I-hats and J-hats together with your motion from chapter 2 and then our unit conversions of chapter 1, and you can do all of these problems. In fact, my little standing joke is, do you want to know the answer to all the homework problems of chapter 4? There it is. There is nothing in chapter 4 that is not answered by that little box right there. Guarantee it. Now, you're going to have to do a lot of work and a lot of deductive reasoning to get to the answer. But this is the thought process. This is what I've pointed out and will continue to point out on the top of the syllabus, so you'll see it on the top of your test. Physics is about knowing how to apply a few powerful fundamental concepts to explain a universe of phenomena. I think you would agree that it's not a whole lot to ask for you to memorize that box. Nonetheless, you will probably still spend 15, 20, 25 hours on the homework trying to do these, because you're going to start there and you're going to think it through and think it through and think it through and realize that's wrong. to start over again and think it through and think it through and then hopefully get the answer after that. So a lot of deductive reasoning, a lot of thought process will hopefully go on. It'll take quite a bit of time, but at the same idea, never forget that they're not complex ideas. And that's the beauty of physics, that we are looking in terms of us scientists and physicists, what is the underlying basic laws of nature? And nature actually does very few laws, very few, like the law of gravity, explains so much in the terms of the planetary motion, the formation of the planets, the orbiting of the planets, the moons that then orbit around the planets. And so there's a lot of things we can conclude from the law of gravity, but it's really just simple one idea. And that's what you're having here, one idea. We're describing that motion. Well, probably the best thing I can do then, besides tell you that is the answer. Let's start working with the answer. Let's do a case. If you remember chapter 2, the first example we did is say, all right, let's pick probably the easiest case. What if the acceleration is equal to a constant? You remember this? And didn't we go through and work out the equation for position and velocity? I guess velocity first, then position. Under the special circumstances that acceleration is a constant? Let's do it again. Same thing we did in chapter 2, except now we've got two-dimensional motion. So we'll be doing the same thing, but twice, right? And hopefully we won't be surprised. We'll end up with the same answer, just twice, right? And so let's see what happens here. Let's ask this. If you are given a constant acceleration problem, and you are asked to find the equation for velocity, how would you get it? Well, looking at here, it says take acceleration, you integrate it, or antiderivative, and you get velocity. All right, so let me integrate this acceleration vector. Now let me point out, I've erased it. No, I guess I haven't erased it, but over here, you guys took a derivative for the first time in terms of a vector. I would say this is the first time you're taking an integral of a vector. But just like, even though it was the first time you took a derivative of a vector, you really thought it was a linear operator, it wasn't that hard. Let's do the same thing here. Let's take an integral of a vector and say this can be written as ax I hat plus ay j hat. And in fact, once we break it in those two pieces, you begin to see that we really are doing the same thing just twice. We're going to have two integrals here. Literally, two integrals. One representing x and one representing y. And so I would have the integral of ax I hat dt for the first one. And the second one, I would have the integral of ay j hat dt. And so again, I'll say you haven't taken a derivative, or excuse me, an integral of a vector, but break it apart and you can see that it's not any different than just your regular functions you learned in your Calculus 150. It's just you're doing it twice because you've broken it apart. So you can't put the I hats with the j hats, which is actually good. That is the whole point of this mathematics, where we won't put I hats with j hats because that's how nature treats them. But as I look at this, how would I do this integral?
Bring the hat up front.
I would say that both of those are constants now. See, when we did it in chapter 2, we said we could pull a out in front because it's a constant. It's true, and we will still do that. But added to that, as I heard somebody say, is the I hat is also a constant, and I'll pull that out in front. And so what I have is ax I hat integral of dt. And following that same logic, for the second term, I would have that integral. And so let's see what I have so far. I have an ax with an I hat. And let me now do the integral. What is the integral of dt? T plus a constant. Especially after the lab we did on Monday, you're never going to forget the constant, right? All right, so t plus a constant. And I guess we can write that constant in different ways. Let's talk a little bit about it. But again, like the lab you did on Monday, you got to think about the meaning of that constant. And then if you actually did an experiment like you guys did on Monday, then once you get the meaning of it, you can also then probably get the number for it. And we're going to see that same approach. We'll at least get the meaning of it right now. We didn't do an experiment, so we're not going to get a number. But we soon will. Yeah.
You have to keep the constants separate for ax and y.
Yeah, and one thing that you'll notice here right away, and I'm glad you saw it, even though you've never done an integral of a vector before, you will hopefully catch right away that constant here and a constant here are required because I have the two integrals, two constants, but I can't combine those constants together to make one. Why not? I don't have like terms, right? This has an I hat in front, this has a J hat in front. And we did an integral in chapter 2 where we had done the two pieces and we had said, hey, I got a constant from that integral and I got a constant from that integral, but let's just put them together. Well, you could because they were like terms. But again, if you're going along and doing your algebra, you'll notice in chapter 2 they were like terms, so we combine them. And you'll notice in this one they are not like terms, so we can't combine them. Same logic, but different results. Again, that's why it's so important. You're thinking about each step. You're reading each step, not just doing it. What does each step mean along the way? And in fact, you could probably write this something such as this. AXT plus, then I'll just make a little dotted line. Of course, it would be AX plus this constant. But the big piece I want to separate out is the I hat, right? Because everything in this little box here has to do with the motion in the x direction. Whereas over here, I could do the same thing, an AYT plus, and I'll put a little dotted line here, and we'll talk about that. Obviously, that should be AY times that constant of integration. But I don't want to just leave it as a constant of integration. I want to understand what it means here. So I'm going to leave a little space here. But I do want you to see before I get to that little space that what I have is this little piece of it would be describing everything that's going on in the x direction, and over here everything that's going on in the y direction. And so I guess I would call that whole thing, isn't that the velocity in the x direction then? Right? I mean, isn't that what we're trying to solve for? We're trying to solve for the velocity. And we said that the velocity here is a vector, and so the velocity would have two parts. And so as I compare the I hat with the I hats, they got to match up. And so this whole description is really saying that is the velocity in the x direction, and that is the velocity in the y direction. And then knowing that, look carefully. That would probably tell you what goes in this box here. Right, if I put time equals to 0, that one goes away. So the velocity becomes whatever's in that box. So what's in this box must be the velocity when time equals to 0. Let me do a double subscript. Now again, I hope it doesn't get too complicated and look that scary when you see this double subscript, because if you're just reading along, it shouldn't. It would make sense to you. They're not like big words you don't understand. You understand these words, right? And so I'm going to put velocity, but notice the double subscript. I'll put an x because it has to do with the x direction, but I'll put an I because it's initial. Same thing here. If we study this, wouldn't this be the velocity initial in the y direction? And so again, notice we have two initial velocities. Actually, there's just one initial velocity, but it has components, right? It has how much does it initially move in the x direction and how much does it move in the y direction. Fair enough? And did you notice then we just did chapter 2 twice, right? In chapter 2, we just got one initial velocity. because it only had an x direction. Now we have two. We have how much is it moving initially in the x direction and how much is it initially in the y direction. And in fact, maybe right under here I should put, like we saw before, equation 1. And if I separate it from the I hats and the j hats, I'm hoping you will see exactly the same thing we saw in chapter 2, didn't we? Does that equation look familiar? Doesn't velocity equal initial velocity plus acceleration times time? Of course, when we did that before, we only had one equation because we had only a motion in the x direction. And so what I'm essentially saying is our equation, which we called equation 1, which we've already committed to memory, we just have to double it. And so take what you've already learned, and it shouldn't be hard just to say, put a subscript with it. Is this motion in the x direction or is this motion in the y direction? And you have both of those. And that's what this little equation is telling me. In fact, let me continue. Looks like some of you are getting cold. Should I turn this back up? It only says 70, but I'll go. Maybe I should go up a little higher. I just get so hot up here. It's just so exciting. I mean, what can be funner than spending a Wednesday morning solving a bunch of physics problems? Oh, I got it. Friday night solving a bunch of physics problems. Okay. All right, well, I'll let you decide that. All right, so moving along here, let's again do the same thing here in this chapter 4 that we did in chapter 2. But again, notice, it'll just be twice. And so what we did after we got to this step, you might recall, is we said, could you give me an equation that describes the position of an object with a constant acceleration? And of course, using this little diagram here, I hope you can, I would then integrate it again. So let's integrate it again. Let's say the position vector is the integral of the velocity vector. And I guess that would be its short form, because those little arrowheads really mean that there's an x component and a y component. And so this really means velocity in the x I hat and velocity in the y j hat dt. And this velocity in the x direction is what we just got after we did that integral. And so put that into here. This would be Vx initial acceleration xt I hat dt for the first integral. All right, that's that first one right there. And this one here is initial velocity in the y direction plus acceleration in the y direction times t j hat dt integral. And so that's what we've been saying. Even though this is only the second time you've probably integrated a vector, again, just like taking derivative, separate into its two pieces. Then the I hats and the j hats you can treat as constant. And then we're just back to the regular functions that you learned in your Math 150 class. And so let's do that integral. Well, I'm also hoping this integral looked very familiar. Isn't this the same one we got in chapter 2 when we did constant acceleration and integrated the same twice? Didn't we look at this and say, okay, what's the integral of that one? Initial velocity multiplied by time. Okay. What's the integral of that one? Ax t squared, and then I'll put the half in front. Each of those should have an I hat with it.
And a constant.
Good. And each of them should have a constant. Now, should both of them have a constant?
Yes.
Can I put those together?
No. Yeah.
I'd say I could in this case, right? Aren't they each inside of the I hat? Now, in a minute, I'll do that integral and get some constants. And that'll have a j hat. So could I put those constants together here? No. But I would say this gives me just one constant. This is maybe constant 1 plus constant 2. Right? I would get a constant with here and a constant with there. And although I don't know those constants individually, I know when you combine them together, there's some other constant. Which again, we never want to leave it just as a constant C like you did in your math class. We want to step back and read it and understand it. And once we get an interpretation of it, let's change its symbol so we can remember what it means. And that's exactly what we did here. We figured out what it means and gave it a symbol for that. And I'm going to do the same thing in just a second. But as long as I'm on this trail, let me do this set of integrals. So that was these two integrals. I've got two more to do. And so I would have a Vy initial t. I would have a 1/2 Ayt squared. Each of those would be inside of the parentheses next to the j hat. And each one of those, as you pointed out, would have a constant with it. So I would have this first term plus a constant, and this term plus a constant. Those two plus constants can be put together. If you want to call this a constant, where that constant is made of number 3 and number 4, fine. But I can combine 3 and 4. And maybe I will call this constant 5 and constant 6, but I want you to see then, although I can put 1 and 2 together to make 5, or 3 and 4 together to make 6, could I put 5 and 6 together to make just one constant out of this? No, that's a step I can't do. That's a step where the math is saying this is an I hat, this is a j hat. These constants aren't like terms, but these are. And see how I'm just following the rules of mathematics? Even if I've never done this before. Right? Just that's my algebra. Like terms can be combined together. Unlike terms can't. Right? Integrals. Never integrated a vector before, but I know it's a linear operator. So if I have two things added together, I can separate that into two integrals. And if I have constants, I can pull them out in front or out in back. All those wonderful properties I learned in my mathematics, I apply it. And our rules that we use for symbolism, like the units and the I hats, all follow the same rules of mathematics. They're purposely set up. They're the best way to describe it. That's the only way they would make logical sense anyways. And more than that, once they make logical sense, they follow the same rules. How beautiful is that? I haven't asked you to do it, but then I bet I could even take the log of an I hat vector. Even though I've never done it before. And let's not do it now. Okay? But that's those two pieces. And so really you might say I have 4 integrals here, right? These first two, which are like terms, I combine together. These are the constants together, and then these two. And so that's what I've ended up with. And in fact, if I study this real carefully, so there's my position vector. What would you call all of those together? Those 3 that are inside of the I hat. Yeah, that's the x, right? That is the x position of it. What would I call all these? The y position. And then knowing that, as I study this a little more, what would I then call this C5? Right, if I put in time equals to 0, that's 0, that's 0. So at time equals to 0, x is whatever that value is. So why don't we get rid of the symbol C5 and call it x sub I, the initial x position. That will help me remember what it means. It's the initial position of it. And then I can do the same thing over here. What does that constant give me? The initial position in the y. And of course, in the real world, you can see why these numbers now can't be combined together. This thing's going to start at some initial position. And it would have a 2-coordinate system. It would have an x and a y. But doesn't this really come out to be the same equation? Does that look familiar? Isn't that the equation we had in chapter 2? And then notice we just have that same equation twice. And so I have said it many times. This chapter is doing chapter 2 twice, right? Here is our chapter. It's exactly the same equation. I bet you already have it committed to memory. The only thing I'm going to ask you now is remember that you have it twice. You have once involving the x motion, so use the x's. You have another thing going on at the same time involving the y motion. And that's why I left myself this little room here in the box here, is because you were already familiar with this equation. And hopefully it will make it easy for you to memorize, because now you can just take that one you've already learned and then just put subscript x's with it. Instead of just calling it initial velocity as we did in chapter 2, now I'm going to call it initial velocity in the x direction. And instead of calling it just acceleration, I'll say acceleration in the x direction. And then of course we have that same equation then twice. We have this object moving in a 2-dimensional pattern, so we're going to have to apply this equation twice. And that would be the equation there. Well, this game can continue, and I don't think it will serve us any purpose to continue. Do you remember the next step we did in chapter 2? I'll give you a hint by saying we came up with equation 3. And how did we come up with equation 3? Yeah, what we did is we said, look, equation 3 is one that's kind of useful because it doesn't have time in it. What we could do is we can solve equation 1 for time and put it into here. Do you remember what we got for equation 3? That's a long way of saying, let me not do it again. I think our time will be better spent looking at some other examples and calculation. But let's put it on the board. What did we get? Didn't we get final speed squared equals initial speed squared plus 2a times, yeah, the distance traveled. What do you think would be different now or added to? There'd be a subscript there, and we would do it twice, right? Not only would we solve this one for time and put it into here, we could solve the second of the first. Maybe I should call it 1b or something. We could solve that for time and put it in here. And what do you think we would get? Yeah, exactly the same equation, except you would have y's instead of x's representing the vertical motion. And therefore, what do you think I would get when I did the fourth equation, which, remember, was solving this for acceleration and putting it into here? Of course, I would do it twice. I would solve that one for acceleration and put it into there. And so when we did it for the x motion, we got that. The only thing I would add would be the subscript x. And so the initial speed in the x direction added to the final speed in the x direction divided by 2 multiplied by time would give me how far did it travel in the x direction. Yeah.
For equation 2, could you just call it r sub x and r sub y to keep it consistent?
Oh yeah, if you like that, and some books do. I don't think ours does. Maybe, but if you wanted to call this r sub x and r sub y, I like where you're going with that. It's consistent with its other notations. Yeah, and maybe I like that better. I do kind of like how it's very clear it's an x, but so would r sub x. And then each one would have a double. Well, that one doesn't have a double sub, but yeah. And some books do that. Ours doesn't, but yeah.
Would that be a minus in between the Vx and
No. No, it's plus sign. I'll do the algebra again if you want, but okay. Yeah, okay, yeah.
Even though both you and the book use subscript I, is it okay if we want to use subscript not?
Sure, if you want to use the not. A number of books do.
What would that look like?
A not a NOT and not a KNOT, but an NAUGHT. Is that the right spelling? Not. Yeah. Meaning zero or nothing or beginning. So, yeah, so a number of books do use the not, and I'm sure many of you come with that experience behind you. That's fine. Yeah. And so this last one here would be the motion in the y direction. All right. So let me just kind of recap here. Did you kind of catch what I've done? And that is we have motion. Now motion in 2 dimensions. And the way to answer those is remembering we'll just do 1 dimension twice. If it is a non-constant acceleration, or for that matter any problem, this is the answer to everything involved. These are how they are connected together. These 4 are special cases. But they're special cases that we've done so often that we, talk about them at the beginning. In fact, I think, like I said in chapter 2, I think we do constant accelerations so much that students think everything is constant acceleration and that these 4 equations are the more important than that. But they're really not. These are just these special cases. So as we've got just a couple minutes left here, let me just kind of set up one example. Many of the problems you are going to see are going to be just simple ones like this. There's an object. I'll take an eraser. And it starts off, and there's a little push. So there's some initial speed at some angle. What is the equation of motion? Could you write down the position of that? So I could say, here's the object. I'll make a baseball instead of an eraser. Man, it's a little early for baseball. Basketball, there we go. So shooting a basketball, all right? And so as I shoot the basketball, I am firing it with some speed, initial speed, okay? At some angle theta. Could you mathematically describe then where is this object? And then of course we'd ask questions like, does it have the right speed to make it into the hoop? Does it have the right angle? Or what would be the right angle and the right speed to make the basket? How long would it make the basket? Or if this is a football and then we, does it go over the goalpost or does it not make it over the goalpost, right? If it's a baseball, we want to know its description. Did it go over the home run fence or not? Where did it land? And doesn't all of this give it to us? I mean, the first question I would ask is this a constant acceleration problem?
Yes.
Yeah, I'd say yeah. Tell me the acceleration though. What is the acceleration for this problem? Good. Some of you are answering exactly what I want you to say here is there's components to that acceleration. There's not just one answer here, right? This is a 2-dimensional motion. And how the ball changes its speed, that is, how does it accelerate, would have an x component and a y component. And I think you learned that in 102, and I am glad you are telling me that the acceleration in the y direction is that negative 9.8 meters per second. We like to write it as negative g. Right? That's the acceleration, but that's in the y direction. That hasn't changed. We learned that in the first lab when we dropped Bob. Actually, we were told it in class and we did calculations first. Then we did the first lab a week ago Monday and we dropped Bob and we came up with those numbers. So we know that's the vertical acceleration. And just because it's moving horizontally, does that change anything vertically? No, that was exactly the point of all these experiments. So we still have the same acceleration in the y direction, and we can even answer this one. What about the acceleration in the x direction? It's zero. It doesn't have anything, right? Does gravity pull anything left or right? Doesn't gravity just pull it down? Didn't you watch this ball fall? Didn't you watch Bob in the lab fall? As Bob fell, didn't it gain speed in the vertical, but what did it do left and right? Nothing, right? So that is telling you that the acceleration in the x direction is zero. And as this thing goes through the air, it always has that acceleration. So yes, this is a constant acceleration. And to describe its acceleration, I have to give both the components. What is the acceleration in the x and what is the acceleration in the y? What are those two? Now, knowing those, and knowing that it's constant acceleration, can't I use all of these equations, these four equations? And since I'm asking you to give me the equation for its position, I'm thinking about number 2 here. Let's write out the equation for where this basketball would be in the x direction. I'll start off with x equals initial x plus initial velocity in the x direction times time plus 1/2 acceleration in the x direction times squared. That's the general equation that should be applied to this, and so let's apply it. Maybe I'll start with the first one, initial position. What is initial position? Okay, good. This is where you have a choice to make, right? All I've given you is the velocity and the angle. I have not given you a position for the origin. So you get to pick that, right? Freedom of choice. But once chosen, it has power over you. Again, hopefully you notice that little trick in the lab, right? That the author of that lab deliberately made the positive direction opposite of what most of you thought should any normal person would have picked as the positive direction. And the point was, so you would see that on the graph. And when you finally got your graph and you had the acceleration kind of going up, you had position dipping down. And it's like, what? I thought it went out and back. Yeah, it went out and back, out being the negative direction. Now, what idiot would pick that as the negative direction? But it was to see if you were paying attention, to see if you were reading the plots. And so same thing here. As I've been saying, you have the freedom of choice, but once chosen, it has power over you. And so be careful that it hasn't already been chosen. And I would say in this case, the origin has not been chosen. And so if this basketball is going to go up and land in a hoop here, and the ground is here, you've got a lot of things. Where do you want to put the origin? Your choice. But just make it real clear you're picking it. And then stick to that choice. Don't change it partway through. Well, that's where most mistakes are made. That students halfway through, not realizing they already made a choice, or not realizing that they're making a second choice, foul up their origin. Or some other choice that they've already made. All right, I heard a couple of you say, and whoops, I guess we got to finish here. Let's put the origin where we launch it from. Okay, so it's not on the ground, it's not as high as the basket, it's wherever the player is, right at the release point here. The reason for that is that would give me a position of 0. And it's nice to have zeros in my equation, so I do agree, that's probably a good choice. What about initial velocity in the x direction? Okay, you got the idea. VI is the total speed. I don't want the total speed here, I want the x component. How do I get the x component? Multiplied by cosine of the angle. What would the acceleration in the x direction be? 0. And so I would say that as being my first equation. Where is the basketball on the x-axis? And we are out of time, but I'll just put it here. Y would be what? Initial position would be 0. What would be initial velocity in the y direction? Sine theta, good. Times t. And acceleration would be? A negative g. And so that would be my equation for the basketball in the vertical direction. And so there's all kinds of crazy questions, and we will ask a lot of crazy questions. All right, so we've got a lot still to do in chapter 4.